In the beginning lectures on Newtonian Sobolev functions, we wanted to motivate their definition by going back to what is called the ACL characterization of Sobolev functions in the Euclidean space. And that characterization says a measurable function belongs to W1P if and only if it has a representative such that it is absolutely continuous on almost every curve parallel to the axes, so in all directions. And that now that we know they are absolutely continuous, they have partial derivatives, and if we collect those partial derivatives and form a formal gradient, that belongs to LP, as does the function itself. And then we defined upper gradients, mimicking that by saying that a function g is an upper gradient of another function if for every curve the values of the function at the ends are far away by no more than integrating that Borel function g along the path gamma for every rectifiable non-constant, well, constant will also work trivially, rectifiable curve in X. And then we defined our Newtonian functions by saying that a measurable function is in N1P of X if, well, X is equipped not just with a metric but also with a measure if U belongs to LP, so the P integral over X of d mu is finite, and U has an upper gradient G with integral of G to the power P d mu also finite over X. So, but at this point we have moved far from the absolute continuity over path story, because the integrability condition here is an area integrability with respect to d mu measure. And we did actually prove already in some of the lectures that I will put in the description that if we happen to know that integral over one specific gamma of this upper gradient is finite for a fixed gamma, then U is absolutely continuous on gamma. And that by definition means that composition of U with gamma, which is a real valued function on a subinterval, compact subinterval of R1, is absolutely continuous in the classical calculus sense. Therefore, every time we have one gamma along which this is finite, we get absolute continuity on that. But do we actually have this for any gamma or most gammas? From the fact that my function is integrable on the whole space with respect to this area integral, do I get that it is actually in one-dimensional integrable along curves? And that is true. And in the classical Euclidean sense, these were famous results by Fugaledev from 60s. And the metric measure setting, in the metric measure setting, we can describe it this way in this lemma, that if you have a function, a Borel function, say, which is in LP of X, then for P almost every curve gamma in X, that is a compact rectifiable path, also non constant, although the claim will be true for constant functions trivially, constant curves trivially, then for p almost every gamma in x, integral over gamma, let me write it nicer, integral, so g ds will actually be finite. And remember, p almost every curve means those curves which violate this condition have p modulus 0. Remember the being upper gradient did not have anything to do with the measure, it's a metric thing, but this integral has to do with measure mu, and so does p modulus. P modulus, remember, is the infimum over all admissible functions, say h, of their LP norm, but with respect to d mu. That is where mu enters the p modulus story, so this condition has to deal with mu, as does this one. So it's reasonable that they are connected this way. So this is a really nice and elegant result. Even in the Euclidean setting, this is quite interesting. So if we put these facts together, fact 1 and fact 2, we see that if u is in N1p of x, then, well, g is in LP, the upper gradient of u, and lemma says that it has finite integral along almost every curve, and fact 2 says then it is AC on almost every curve. So then u is absolutely continuous on p almost every path, rectifiable compact path in X. And that is the kind of message of this lecture. So finally, after definitions of N1p spaces, after defining modulus, which was necessary to even be able to state this result, we finally have fulfilled the promise of duplicating the ACL characterization of functions. It's not a characterization per se because the backward direction is not easy to formulate in metric space. From the fact that you are absolute continuous on almost every line, it's not easy to produce an upper gradient because you don't have a canonical way of comparing path to path. You don't have foliation and stuff. But anyway, the message is still there that the key feature of Newtonian Sobolev functions is their absolute continuity along almost every curve in them, which you can use to rule out certain functions from hoping to be in Newtonian class. Let me talk a little bit about this lemma 1. I said it's already interesting in Euclidean setting. Let's say you have just R2 and take a box, say, and you know that integral of f with respect to the Lebesgue measure L2 is finite, right? From this theorem, where p is 1, we see that the integral is finite along almost every curve. So along almost every rectifiable path, this one-dimensional integral will be finite. This is much stronger than what Fubini's theorem could give us because, in fact, I think a little bit underemphasized aspect of Fubini's theorem in undergrad courses is that we get finite integral along the foliation curves at all, because usually we emphasize the equality in Fubini's theorem, but even before the equality itself, it's kind of amazing that from the fact that you have L2 integrability, you get L1 integrability along almost every path. So let's say This is the curve at height y. Fubini says that from 0 to 1, without loss of generality, integrate along this gamma of g dl1, which is just ds, and then dy. We say, we know this is equal, but again, let's say I'm just only interested in even like wiggly up to a constant fact that this is now I'm having f. So f dl2 over r2, which is finite. And now that this integral is finite, it means that for almost, in particular, it means that for almost every y in 0, 1, integral of f along gamma y ds is finite. Of course, this cannot be for every curve because you can go and artificially switch the values of f along this one curve to infinity. That wouldn't affect this one, but of course, the integral here will no longer be finite. But Fubini says that except for a negligible L1 negligible collection of points, the integral is actually finite. What lemma up here says more is that even for many more curves, we have the finiteness of this integral. They don't have to be parallel to x-axis. They don't even have to be straight lines. So I won't pursue much nuanced properties of Newtonian Sobolev functions. A few more videos on Poincare inequalities. This is something I am actively working on recently. And therefore I will go back to some of the examples we've seen before and discuss Poincare inequality a little bit. And after that, I am open to starting some new topic, and I'll put a poll to ask for your opinions as well. Probably we could also have a live session where we get to meet each other and probably discuss mathematics and life. Until then, have a great one and thanks for watching. Please also subscribe. I see that a lot of people who are watching have not subscribed, which kind of I suspect that makes YouTube to not recommend the content as often as it should.